I'm going to talk about zippers, which is a way to navigate trees with functional style. This is live code running here, so I can edit it and make any changes, and we can see the result. So if you've got questions, anything's unclear, we can play around with it and see what changes. So I'm going to do my examples. Alright, so I know we're a multi-language group, so I'm going to not do a language intro. The ideas here apply in any language, functional or not, and they go back about 20 years. And it's not, so I'm going to be using Clojure, a dynamically typed Lisp language, but if you're a static typing kind of person, it works perfectly well there. The original was in OCaml. So compared to kind of naive, mutable, or iterative API like you might get in something like Python, zippers give you efficient functional updates as you navigate. So in Python, if you've got an iterator over a sequence, you can't edit that sequence as you iterate over it. Alright, so the other thing the zippers have that's cool is you can navigate any direction. So you can go around your tree, forwards, backwards, any way you want. And at the end, I'm going to have a real-world example of how we use this here at Scenics. But for starters, I'm just going to give toy examples just to keep things simple. So you're only going to need to know a few things about Clojure to go through this. So the first thing is that square brackets indicate a vector. So it's a list of items. They don't need to be of the same type, and it's efficient to add to the back, that sort of thing. If you see a colon and the blue text there, that's a keyword. And those are kind of like immutable strings. In Clojure, they're used to represent data a lot. And there's a few other tricks, but we don't really need to know. And then if you see curly braces, that's a map. It's a key value store. In Clojure, it's kind of the Uber data structure, and similarly, no need to have the same data types there. So if you've never used a Lisp language, all the code is held within parens. So the first thing is your function you're applying, and everything after that, separated by spaces, is the arguments to that function. So here we're calling the plus function with the arguments 1, 2, and the result is 3. To make things a little bit simpler, so you don't get astounded by the chain of parens, I'm going to use this syntax for chaining function calls that's built into Clojure. So you can read from top to bottom. 1 is the first argument to the plus 2 function, and then that gets passed into here, and the end result is 5. So if I run those again, I can change the numbers, and it changes the end result. So we'll be using this throughout, and that's basically all you need to know about Clojure to get this. I mean, just got to run this. Don't need to know about it till later, if at all. So our example tree here, I have a little picture, is held in this vector. So it's got the number 1, it's got AB in another vector, 2, 3, and then 40, 50, 60 in another vector. So in the picture, every time inside the vector there's a single item, it's a leaf node. If there's another vector, that introduces one of these branching nodes, and then any single items in there are leaf nodes. So the entire vector itself is this node here, that's the root. Then you've got 1 as a leaf, this intermediate node, A, B, and so on. So I'll be using this, I'll keep the picture around, we'll be navigating around that tree as we go. And I would like to keep this on top, but that's apparently next to impossible to do on OS X. So you gotta like disable all the security features, and I don't like that. So it'll be dumb, I have to keep going back. A zipper is a pair of the current location and the navigation state in your tree. So we've converted that initial tree into a zipper here. So your current location is the entire tree, the root, and then your navigation state is nothing, because you haven't started to navigate yet. So location is pretty intuitive. We'll see that first thing in the vector update as we go along, but the navigation state needs a little bit more explanation. So if we navigate down from the root of the tree, that takes us from here down to the 1. So our location is now updated to be the 1, and our navigation state is now this map with a bunch of data in it. So the first two things are L and R. Well, conceptually the first two. So L is what's to the left of my current location. So to the left of the 1 is nothing. To the right of the 1 is, well, all the rest of the tree. So the AB node, the 2, the 3, the 40, 50. And then the other two keys, the most important one is P path, which is short for parent path, and that'll track the navigation state as we go deeper into the tree. The second is an unnecessary optimization that the closure implementation has, that's the parent nodes. So this basically stores, it's a stack of your navigation into the tree before any modifications. So if you navigate through the tree and you don't make any changes, it can just return this back to you and then not have to recompute the tree. So
sorry, when you navigate, when you do the down,
yep.
You always go to the first one on the left?
Yes. So if you have the choice of there's multiple things below your current location, it goes the leftmost. So we go to the right, so that moves us from the 1 over to this node here. So now it says your location is the AB branching node. To the left is now the 1. To the right, the AB has been popped off. We just have the 2, 3, etc. And the other two keys are the same. So to watch a little bit how the navigation state changes, I'm going to do a depth first search to the tree. So Clojure's built-in zipper library has a single function that moves you through your depth first search. So starting from the top, we say go to the next node. That takes us down to the 1. That's the same as it was before when we did the down. If we do next again, it goes over to the right because there's no children of the 1. So again, the same navigation state as before. 1's to your left and everything else is to the right. So if we call next again, we start to see the nesting happen. So we've moved from the AB down to the A. So it says there's nothing to the left of the A, the B is to the right of the A, and now the parent nodes includes the entire tree plus that AB branching node that's here. Has been added onto the stack. The parent path key here includes the old navigation state from here. So it says 1's to your left, 2, 3's to your right. The P nodes of this state is the entire tree. So every time we go deeper into the tree, it's going to add another nesting of this map. So we go next again from the A, takes us over to B. Location is B, A is to your left, nothing to your right. So now we'll get into some of the downsides of using zippers. So the navigation state nests increasing as you go through the tree. So the memory usage is going to scale with how deeply you navigate into the tree. So if you have a tree that's 100 levels, 1,000 levels, 1,000,000 levels, whatever, you're going to have to keep increasing the nested state that you store here to keep track of where you are and how to get back up to the top. But if you never navigate into those deep levels, then you're safe. So if you don't need to, you won't pay the cost. But if you spend a lot of time navigating around the very millionth level of your tree or whatever, you're going to have a lot of memory usage there. So the other downsides are, again, there's memory when you navigate. So every time you move around, you start to move stuff from your left to your right. If you go down, you increase that nesting. But unlike the nesting of going deep into the tree, your old navigation states can be GC'd. If you're not looking at it, you can just throw that out. And in some languages, you can do fancy tricks like structural sharing to not have to pay a lot of cost to navigate around. And the other thing is that to zip the tree back up, so to get back the original data structure you had, that vector that we started with, it's time intensive. And it scales with the depth again, because you have to pop out this nested structure and put everything back together. And again, in Clojure, it's going to be optimized. If you don't make any changes, it just gives you back the original. But if you do make changes, you have to pay that cost to recompute. So aside from the depth first search, we have the direct navigation functions up, down, left, and right. So if we go down from the root, we're at the 1. We go right, we're at this AB node. We can go down again from the AB node to get to the A. or we can go back up to get to the AB. So if compared to just doing a straight iteration, from front to back, if I'm looking at the A or B node and I decide, oh, hang on, I need to check some information that's up here, I can just go back up, get whatever info I need, come back down and do my processing. So you're not limited in your decision making to just the one node you're looking at, or having to carry around the past states as you need them. You can just go back and forth. And so not only you can go back up, you can go to the left. So I went back up to the AB node and then to the left again. So the other big selling feature is doing updates to the zipper. So the pair is just a regular data structure, a vector with 2 items. It contains the current location and the navigation state, and they're both just simple data structures. So anytime you want to update your zipper, you just make changes to those data structures. So to update the node of the tree that you're currently visiting, I've got a function here, just multiplies by 10. So I go down from the root, over to the right to be looking at this 2. And I say, okay, edit with the function multiply by 10. So now our 2 is changed to 20. And that just updates the current location. All the navigation state's the same. To left is all the same nodes stored before, to the right is all the same. But now it's got this change true key. And so that tells the Clojure API that basically you can't use this anymore, that's out of date. So when you want to get the original structure back together, when you want to rezip it, you've got to compute the changes that have been made. We can also update the tree itself because the navigation state is data 2. So if we want to add new nodes or move nodes, we can do all that as we navigate through. So just undo that. So I insert this new item to the tree to the left of the 20. So if we had another picture, that would just slot in right here. And then similarly, it has this change true key. Hang on. All right. Well, so when I remove the 2 from the tree, the 20 that we had modified, it moves our navigation state back over to the left to the new item we had inserted. And says to the left of us is the 1 AB, to the right is the 3, 40, 50, 60, and it has that change true still there. So it still shows the 2 here that we've removed, and it doesn't show the new item, but once you put it all back together again with the root function, it'll have the final result. So we've added a new item, we've removed the 2, and now it's in its place.
So that P nodes is useless after you change it?
Yes.
You just might as well not even have that.
Yeah, I don't know why it doesn't get deleted, but they carry it around. I looked around, I can't really tell what purpose it serves after you've made changes. But yeah, it's kind of vestigial at that point.
Restoring the original state?
Maybe, but I don't know what you would need the original state for at that point.
Yeah.
When you call this root, what it does is it goes to the most nested level of p path, takes everything on the left, takes your current state, everything to the right, puts that together, goes up a level, just does that over and over. So it doesn't use this at all when the change is there. So aside from our toy example, here's where I got to use this at Scenics. So in 2014, we made a model of the telecom domain that we work in, and all the different entities in that model existed in a tree. In 2015, we made a new domain model to capture the complexity that we were seeing in our new projects, and we changed the tree to be a graph instead. And so we wanted to write some software that would take the old format, convert it into the new. So the initial implementation of the converter used recursion because, well, hey, it's a tree, it's a recursive data structure. But it turns out that a bunch of our entities don't map one-to-one in the new model. So you can't just say, rename A to B and you're done. We had to look at A and B together and use those combined to make a new C, and take D and E and make those into 3 different things. And so, just a simple, okay, we'll look at each node individually didn't really work. Had to go and modify your call stack so that you would have access to any sibling or parent nodes you needed, and carry that through, and it was not easy to make any modifications to this original version. So with the zippers, your state is just data, and it's very easy to track state that way. So I'll put a little picture up. This is a kind of simplified, anonymized version of our original model. So each node is represented as a map, and they have a node type that I'm using here to compute the color. They have a name, that's the label on these circles, and then they have children, which is the branching out here. So the Scenics office has 3 children, each of which is a router, and the kitchen router has a child that's Scenics guest, and the others are inactive. And so with a converter function that you don't have to look at for now, but I can if anybody's interested, we can convert that tree into a zipper. So we've got our navigation state, we're at the root of the tree, or sorry, our location is the root of the tree, and navigation state is nil. I can say, get me the next thing, so it goes from the top down to the kitchen router, same as before. I can go up and down, so go from kitchen router down to Scenics guest, go back up, go back down, and all of the other functions, the depth first search and the edit, the remove, is all based off of these fundamental up, down, left, right primitives. So once we've got these implemented in a very simple way, we can use the entire zipper API on arbitrary structures. And it just does the same thing. If it takes the left, it takes the right, looks at the P path, it's the same left and right stuff as before, puts it all back together, and so that it allows you to look at, okay, well, if I need information from the kitchen router and 4th floor router in order to create new stuff in my new model, I just say go to the right, go to the left, get my siblings. I can do all that stuff really simply. I don't have to go and change the arguments to every single function in the program because it's a recursive function, and it's a mess. So that's zippers.